Hi everyone, my name is Anvita Bansal and today we are back with another lecture, and the topic that we are going to start today is bit manipulation. So the question for today is, let me just show you. Let me check if you guys are. I think we are live. Okay, so let me show you the problem for today. So from your SD sheet, we are starting off with bit manipulation, and the question that I'm going to take with or start with is rightmost different bit. So let's have a look at the problem. So this bit manipulation, you will see that the codes are going to be very simple. The codes are just of 1 or 2 lines, but the logic behind understanding bit manipulation goes deep. So you need to pay attention. The questions are easy if you understand the concept of bit manipulation. Okay, so let's start with this question. You're given two numbers m and n. Your task is to find the position of the rightmost different bit in the binary representation of numbers. So you're given two numbers 11 and 9. Let's take that. So a prerequisite is that at least you understand what is binary representation of a number and how computers or how in the world of programming these numbers are being handled. Okay, so just a little bit of that knowledge is required, otherwise what I'll discuss you'll understand. Okay, so there are two numbers, n is 11 and m is 9. Okay, you have to find the rightmost different bit. Now what does this mean? Let me write it properly. If you understand this question right, so you will be very easily able to do this question. Find first set bit. That's why I have chosen to start with this question, because this question itself will cover the solution for this problem. So let's see now. Your n is 11, your m is 9. You have to find the rightmost different bit. Okay, this means that a number in terms of bits can be represented like this. This is the number, right? So our code analyzes, or it works on binary representation of numbers. Okay, we feed a number of decimal form, but all the operations takes place in the binary. So computer works in binary language, so all the numbers that we feed into computer gets converted to binary form from its, this is decimal form, so it gets converted to binary, and then operations take place, and then it finally, the compiler returns us what the decimal representation of number, or the number which we gave as input. Okay, so internally what is happening, this 11 is getting converted to its binary form. What is that form? To convert any binary number, you can always do this thing. So what is the remainder when we divide 11 by 2? I'm not going to get into its details. That's why I said I expect you to have binary number representation knowledge. Very easy, but I will write it for you. Okay, this is 1. 2 2s are 4, remainder 1. 2 1s are 2, remainder 0. Then 2 zeros and remainder 1. Okay, so 11 can be represented as 1 0 1 1, right? Similarly, 9 can be represented as 1 0 0 1. Okay, this is 9's binary representation. Now you have to find, when you move from rightmost index of these binary representations of both the numbers, so which is that bit, which is that position where you find that the bits are different. If I take this position, both the numbers have 1 as their bits. Okay, move to the next position. This 11 has 1 as its bit and 9 has 0. So this is the position, the first position from rightmost. When I'm traveling from rightmost index, the very first time when I'm finding the bits to be different in both the numbers is this position. So you have to ideally return which is this position. This will be treated as first position, this is treated as second position. So from right you are traveling and basically checking which position you are finding the first different bits. Okay, so this comes out to be this position. So let's see for one more example, another test case that is given in your question itself, this is 52 and the other number is 4. N is 52, M is 54. So 52 can be represented as, again you can try out this thing and I'll directly write it. So 52 can be represented as 110, then it is 100, and 4 can be represented as, I'm directly taking this value from here, you can see in your question. So 52 is this and 4 is 0100. So let me write 0100. All the preceding values can be taken as 0. Fine. So that's needless to say. Now, if you travel from rightmost index, at which position do you find both the numbers containing different bits? So both are 0, move to the next position. Both are 0, move to next position. Both are same, move to next. Both are same, move to next. At this position, I find that the numbers are going to have different bits. So which is that position? This is position 1, 2, 3, 4, 5. So you should be returning 5 as your answer. Okay. Now, how do we solve this problem? So see, we are going to use some mathematical operation. We are going to use some bitwise operations here. Bitwise operations that we are going to use, you need to know at least their truth tables, and even if you don't know, I'll be telling you, and then I expect that you go through what these operations are. Very simple. I have also already taken these operations previously in the other questions. I remember one question of string where we took this OR operation. Okay. Then other one is left shift, right shift. So I expect that you understand what is right shift. Okay. Let's see. So these are some hints that I have dropped for you to know how are we going to proceed with this question. So the very first thing, very simple, not simple, if you know it is simple, if you don't then you need to pay attention. Okay, so whatever number you have, I say that can you find the leftmost set bit, leftmost, not leftmost, the one second. So what is asked, find first set bit. I am just taking you through this question. Why? Because I want to tell you what this question says so that you can relate with what we are doing. So in this question they ask you to find the first set bit of this number when you move from right side. So you have to return the position of first set bit found from the right side in the binary representation of number. Not that we are going to solve this question, we are solving this, moving back. Okay, so why did I show you? If you move from rightmost position, what is the index or what is the position at which you are finding 1? So let me take 52. Okay, so 52's binary representation was 1110100. Correct? Okay. Now tell me, if I move from right position, which position contains 1 for the first time? So this is 0, so move to this position, this is 0. So this position is where I found 1 for the first time. This is basically I am finding 1 for the very first time. Okay, when I travel from the rightmost index, first time from rightmost index. Okay, now why am I finding it? You will understand this once I discuss this part, but let's focus on, because this question, not directly, but this question helps you in further when you do competitive programming. Bit manipulation is very essential part. Secondly, a lot of times it itself is used in lot of algorithms. So this thing you should be knowing such that you can easily do this in one line of code. So now the problem comes down to, and why I am making this problem go down to this part, I will tell you later on. First, we are now trying to know that how can you find the position at which you find 1 for the first time in any number. So one thing to note is, whatever discussion we are doing and wherever I am representing the number in binary form, we are not actually converting the number while we are coding. Okay, while we are coding, we are not going to convert the number actually in its binary, but this is for explanation that what goes internally when we are doing such operations on any integer n. Okay, so let's see what can I do in this question is, if you see a number which is given like this, let me now write it nicely. Any number n is given like this. N is 1 1 0 1 0 0, and I say what is 2's complement of n. Okay, what is 2's complement of n? That means I am asking you to find 2's complement of n. So you should be knowing that 2's complement of any number is basically inversion of that number, add it with 1. That's how you find 2's complement. 2's complement is simply inverse when you are adding 1 to the inversion of the number. Okay, that's how 2 complement is calculated. Now let's see what is, I'm sure you know what is inversion of number, but let's see what is inversion of number. Inversion of number is simply reversing all the bits. If it is 1, you convert it to 0. If it is 0, you convert it to 1. So what I tend to do, I am willing to first convert this number to 2's complement, and then from there I am going to do n and operation of that 2's complement with n. So what I am going to find, that we will see. First let's do it. So this is the number. Let's first write the inversion of this number. Okay, when I write the inversion of this number, it will look like this. All the bits will be converted to the opposite ones. So this will come as 0 0, this will become 1, this is 0, this will become 1, this will become 1. Because I want to find 2's complement, that is why for representation purpose only, I am writing this negation of n. Okay, not that you have to go ahead and do it. You can simply write this statement. Our program has the ability to find the answer for this statement directly. That is the reason we have bitwise operations in our languages. Okay, in our programming languages. So this is representation for 2's complement. This is representation for bitwise and. Okay, so now let's see what is 2's complement. So if I want to write 2's complement, I am simply adding 1. So when I am adding 1, what I am doing, rest of the things can be taken as 0 because I am adding 1. So this will come out when you add any number, what it is. See, 1 plus 1 is 2, and 2's binary representation is what? 1 0, right? So how do you do binary addition? I'm sure you must be knowing that. If not, you can see here. So when I'm adding it with 1, in terms of binary, I'm going to get binary number 10. So 0 will be here and 1 will be carried over. So 1 will be carried over at this. So you have to see that I am adding negation n with 1, correct? Plus 1. So this is when you add 1 plus 1, again becomes what? 1 0. So 0 will be here and 1 will be carried over. So this becomes what? 1, and rest of the bits are going to remain same as they are in negation of n, 0 0, right? So this is finally your 2's complement. Do you see this thing? That finally your 2's complement is what? This. What we wanted to focus on, n and 2's complement of n. Now we want to do AND operation, bitwise AND on n and 2's complement of n. So what will we get from there? AND and bitwise operation. So I am just writing what I am doing, add 1. Fine. So this is what it is. And then you got 2's complement. This is 2's complement. Okay, this is this number. Now your focus should be on this n. I am highlighting it. Let me highlight. So this, let me just do one thing. Now do not see what is here, do not see what is here. Okay, because your target is n and 2's complement of n. Fine. So let us see what do we have. Now we want to do bitwise AND operation on n and 2's complement of n. So what will it be? See, starting from rightmost bit. In bitwise AND, whenever you have two bits of 1, only in that case you are going to get 1. In other cases it is 0, right? So 0 0 becomes, let me write it with red, 0 0 becomes 0 0, this 0 is 0, this 1 and 1 is going to be 1, this 0 and this 1 is going to be 0, this 1 and this 0 is 0, this 1 and this 0 is 0. Now what you can do, you can see that whatever number binary representation of number we got, we have 1 present at exactly that position where in my n originally I had first one from the rightmost index. Do you get this thing? That in this representation, in binary representation of this number, let's say this is number x. So whatever x I found from here, you can observe that I have one only at that, exactly at that position where actually I wanted to find the first set bit, which is this one. So my question was for you to find one when I'm finding one for the very first time when I start from rightmost index. So this is this position. And finally, after doing all of these operations, basically after doing this operation, I am able to get a number which has in which one is present only at that position where I wanted to find it, right? So my task comes down to find which position this one is present at, and I can return this position, which will tell me that n has first set bit at this position, right? Okay, so how can I do this thing? I can easily do this thing. See, so this is binary representation for the sake of our understanding. Actually, this number will get converted to what? 100 is representation of what? So this is actually 00012. So this number is what? 2, right? 0 0, and this is 012 power of 4. Okay, so how do you represent 4? This is the binary representation of 4 only. I hope you know this thing. How can we do that? So you do it 0 multiplied by 2 to the power 0 plus 0 multiplied by 2 to the power of what? 1. Then 1 multiplied by 2 to the power of 2. 2 to the power of 2 is 4, and these things will be 0. So this is actually, if you see, when you do this operation, your function will return you number integer 4, right? Because this is the binary representation of 4 only. Now if you do log 4 base 2, what are you going to get? You're going to get 2. Just add 1 to it. This is the position. So these are some calculations which obviously you can understand only once you solve this problem. I wouldn't say not very intuitive. You just have to have some understanding on bit manipulations. Only then you will be able to get it. So this is how we can see. So this is the method that we have chosen to check that if I do log of this number, then the number that I'm going to get will actually be the position -1 where I want to find 1. So I'll just add 1 to it and I will find this position. Okay, now wait. Coming back to our original question. Our original question was what? So this is 52's representation 110. 52 is 110,100, and your 4 was what? 00100, correct? This was your 4. Now my question was to find in which position does these two numbers have different bits. If I start from right index, which is the first position I am finding at which my two numbers have different bits, so ideally it should be this position. So when I said I'm checking which position I am finding the first set bit, why am I doing so? Because let's do XOR of these two numbers. So n XOR m. Okay, what are we going to get by doing n XOR m? So in XOR's truth table, if you see, wherever we have same bits, my resultant bit will be 0, and wherever I have different bits, my resultant bit will be 1. So if it is 0 0, it will be 1. Okay, if it is 1 0, it will be, sorry, if it is 0 0, it will be 0. It is 1 0, it will be 1. If it is 0 1, it will be 1. If I do XOR on these two bits, answer will be 0. If I do XOR on these two bits, answer will be 1. Same for this. If it has 1 1, then also 1 XOR 1 will be 0. So that's the property of XOR. So if I do XOR of two numbers, so wherever I have same bits, I am going to get what? 0 there, right? So let's see, 0 0 0 XOR with 0 will be 0, 0 XOR with 0 0 0, because both are same bits, 0, different bits 1, different bits 1. So now you know, when I do XOR of two numbers, so wherever I am getting 1, that means that is the position where n and m have different bits, correct? You getting this point? So whenever I find 1, if this is XOR of any two numbers, so one thing is for sure, that wherever I find 1, that means at that position both n and m must have different bits, okay? Must be having different bits, okay? So if that is the case, why not write a function like this, the one that I just showed you, which can tell me that what is the position from right where I am finding the first set bit. When I say first set bit, that means the position at which I am finding a 1. So the first time I am finding 1 from rightmost indexes is this position. So this position is what I want to return. This is position 1, 2, 3, 4, 5. So fifth position is the answer for this entire question. Okay. So let's travel over this question and check once again. So what are we going to do? One more thing. So your n and m, 52, 1 1 1 1 0 1 0 0, and this is 0 0 1 0 0, right? This is 52, this is 4. So I am writing a function which is finding first set bit. So function first set bit, okay, FFS is the function which will be taking some int x, okay, and this will return position of first set bit, okay. And I am actually calling this function from the actual function, that is get first position of rightmost bit. That is the function name, okay. So if you see the function, this is the position of rightmost different bit. So from this function, position of rightmost, okay, let's say this is the function which takes two numbers, int n, int m, okay. Then what I am doing, let's say I am taking int x which is doing n XOR m. So how do you write XOR? I hope you know that what is the XOR operator, bit operation. This is how you represent XOR operation, okay. So this is taking x. Now I am passing this x to FFS and I am basically returning FFS of x. That's what I am doing. As simple as that. And now entire question comes down to writing this FFS function. So what FFS is doing, if you're writing a FFS function, if your n is 0, that means whatever number you are passing. See, now let's do the x. What is the x for n and m? If I write x here, x for n and m is what? N XOR m, okay. So x will be wherever, what is XOR? Wherever you have different bits, that will be 1. Wherever you have same bits, that will be 0. So let's write the x which is XOR of n and m. Let me write it here, n XOR m, okay, that is x. So 0 0 will be 0, 0 0 is 0, 1 1 0, 0 0 is 0, 1 0 is 1, and this is 1. Now actually the decimal representation of this number, whatever this number is, this number will be 0 1 2 3 4 and 5, 2 to the power 4 plus 2 to the power 5. So 32 plus 16, that is 48, okay. So this number is actually 48. Fine. So if you see, number 48 is being passed to FFS. This FFS will be having 48 and then it will be operating over this number and making the calculations. The calculations will be what? It will return n and operation of, I'll tell you what it will return. Let's delete it. fine. So I was writing ffs function. So ffs function, if your n is 0, this 48 is not 0 obviously. If n is 0, that means you do not have any different bits, so return -1. In other cases, what you are going to do, so whatever x you have, you are doing bitwise AND operation of x with 2's complement of x, which is represented like this, correct? And then you are doing log base 2 of this quantity plus 1, as this is going to return you the position. So in Java, the language that we are going to write in, how we handle this case, you know that by default when we use math.log of any number, so math.log is what? It is of base e. Now if I want to write it for base 2, I cannot directly do log 2 of n, right? I can do log 10 of n, math.log 10 of that number, but to convert it to base 2, I will divide, let's say, log 10 of any number divided by log 10 of 2 will actually give me log n base 2. How? You must be aware of log n base m. It is what? You can write it as log n with same base, what you're going to divide it with, log m base 2, right? So I just simply want to, I want to find log n base 2, so that's what I'm doing. Whatever number I have, I'm just simply representing it where n is this, m is 2, right? So that's what I'm doing. I hope you understood this operation. So this we will do while we are coding. So let's go and write the code for this. Okay. So that's the only thing we are doing. I hope you understood this problem. Let me see if you guys have any doubts. Fine. So moving on, let's write the function. So this position of rightmost is doing what? This position of rightmost is doing nothing, but it is making a call to ffs function. What is that function? Before that, it is taking int x as equal to m and bitwise XOR of m with n, right? This is what you are passing. The reason we are doing XOR is that wherever I will have different bits, I am going to get 1 at that position, right? Because 1 will be found only where I have different bits. So when I will have any number of this type, 0 0 1 1 0 1 0, let's say this is the number that I will have in x binary representation, then I will see that the first time I'm finding a 1 is at second position. So my function ffs task will be, my ffs task will be to find first set bit from the rightmost index. So that position it will return, and I will simply return it. Now let's write the function ffs. So public static int ffs int x. Okay. So if n is equals to 0, you return -1. Otherwise, you return, first let's do the bitwise AND of n and x and 2's complement of x. So that will be x, capital X, and bitwise AND of 2's complement of x, which is this. Fine, that's how you represent it. Then you have to convert the logarithm, and whatever values you will have after dividing log of that with log of 2, you should convert it to that integer, because it might be decimals, so you have to convert it to int. So return int of what? See, I told you log of, how do we take log function in Java? Math.log, and I want to take it of base 10 because I will further convert it to base 2, log 10 of this, whatever you find, int, let me write it, x is equal to, so this x, small x, okay, divided by math.log of 2, right, base 10 and this is 2. Plus 1 is what you should return as position. So nothing, x contains bitwise AND of x and 2's complement of x. Now this will return a number whose binary representation will be of this type. Let me show you. So this small x will have this number. The small x will have this number, that is n and 2's complement of n, that is 0000100. So you will observe that I will have 1 only at that. So wherever I have 1 in this case, that will be the first set bit. Fine. So I will find 1 will be only present at that position where I have 1 in that number from the rightmost index. The first occurrence of 1 from rightmost index will only have 1 in this final representation of n and 2's complement of n. Okay, so my task is to find this position. So this position can be found by taking log of actual decimal of this number. So the decimal representation is 4. If I take log of 4, that is 2, and actually I want to return 3 because that is where my 1 is present. So I'll do plus 1. That is the reason I am doing it. Okay, so that's what I will finally return. Let's check. And math.log plus 1. Capital X. Okay. And that's how you solve this problem. So if you copy the same logic in this problem, so if you copy the same logic in this problem, except that they expect you to return 0 if your n is 0 and rest is same, you will be able to solve this problem also. If there is no set bit, then return 0. That is why I have made it to 0. Otherwise, you will, for this question, you are doing it minus 1. Okay. So I hope you understood this problem. There is also one more way in which you can solve this problem, which is if you let me just show you that the question says that you are keeping the track of at which position in XOR. Okay, 1 second. So where is XOR? Okay, the other approach that I am discussing is also very simple, second approach. So you are passing this XOR number. So the first position you are finding 1 is at that position you have to return. So what I am doing is I am doing right shift each time. Right shift, how do we do? I am simply doing it. It's this numbers bitwise and with 1 each time. So until and unless I get a 1, I am going to shift the number by 1 bit every time, and once I find that it is 1, that means that is the position and I am keeping the track. So how am I doing it? Let me show you. So second approach says I am using right shift of the number, which is, how can we solve this problem by this method is that you have n, you have m. Okay, you do n XOR with m, so you get a number, let's say x. Now in x you will be only having, x will be containing 1 only at that position where n and m have different bits, correct? Okay, So your task comes down to finding which position that 1 is present when I start from rightmost index. So first time, the first occurrence position, you have to return position, that is the first occurrence of 1, occurrence of 1 in n XOR m. Okay, starting from right. That's what you have to do. So n XOR m, I am taking it 1 1 4 times 0. So this is 1 1 1 2 3 4. Now what I am doing, now see that task of right shifting starts now. So this is your current number, let's say x. Okay, so with in your x, let's say you initialize a position with 1. Fine. Now you do bitwise AND with 1. Okay, so when you do bitwise AND with 1, rest of the elements will be 0. This is again for representation. Actually we will be passing just numbers. Okay, and I am doing x and 1. So x and 1, how it is looking like, finally you will get 1 only at that position where you will have 1 in both the numbers, but 1 0 and will be 0 0 0 0 0 0. If x is 0, if x is 0, this means what? See, if x is 0, that simply means that there was no bit, that means you did not find 1 at the rightmost index. It simply means this, because actually you have taken 1, and 1 with any number, if I am doing its AND, with any bit if I am doing its n, and so only if it is 1 I am going to get 1. So if your x is 1, that means you found a 1. If x is 0, that means you have not found 1 so far. So you are going to do a right shift on the x, whatever x you had. So how you are going to do it? So x will become x right shifted by 1 position. So your now your new x will be like this. See, keep now your new x will look like this. When you right shift a number, you are actually multiplying that number with 2. If I say, so if you multiplied with 2, whatever number it was, when I multiplied with 2, whatever I get, that number's binary representation will be like this, which means the last bit will be removed. So shift each bit by 1 position to the right. So what are you going to get? This 0 will come here, this 0 will be 0. So you are going to get a number like this. If you remove the last bit from this number, you will get 0 in the end, other 0, third 0, fourth 0 is removed. Then you have 1, 1, and this will be 0, right? Because each bit has been shifted by 1. This is the right shift on x. Okay, fine. So new x becomes this. Now you are doing again its AND with 1. So its AND with 1 is going to look like what? 0 0 0 0 0. Its AND with 1 will be 0 only. Every rest of the things also 0. So again your x has come out to be 0. Let's say whatever it is, not x and 1. New x is again 0. Not x, you do it and let's say a. Okay, so your a is 0 again. So do the right shift one more time. Until unless you find a 1, keep doing right shift and your position will also be incremented. So here your position was 1. When you found a to be 0, again you made a right shift on x, so position incremented by 1 again. So position became 2 this time. Now again do a right shift on x. So x is going to look like what? This was your x. This bit will be removed and every bit will be shifted to right by 1 position. So now you have 1 0, other 0, then 1, then 1, 1 0, and 1 more 0. As many shifts will be removed, that those many zeros you are simply putting up here, right? So now again your new x is this, and do its AND with 1. When you do its AND with 1, what are you going to get? So a is going to be again 0 0, because 0 0 0 0 0 0 0 0 0 0. None of the 2 bits are 1, that is why a is 0. Since a is 0, again do a right shift on x one more time and position will also be incremented. So now your position will be incremented to what? Position becomes 3, and you are doing again right shift on x. So x will be what? Now your x becomes Again remove the last bit and shift by 1. So this will be 0, 1, 1, double 0 and one more 0. Again do its AND with 1. Your A is going to be 0 again, right? A is going to be 0 because again 1 AND with 0 is 0. Rest of the values will also be 0 only. Correct? So you found A again 0. First of all, increment the count of position and then do a right shift on X again. When you do a right shift on X again, you remove this last most bit and you get 1, 1, triple 0 and one more 0 added. Do its AND with 1. Now is when you are getting 1 in your A. Rest is 0. But what is this number? This number is 1, right? So when your A becomes 1, that is when you must have updated your position with position has been incremented by 1 again. Position becomes 5. Now your A is 1, so you will not further do X right shift. That will not happen. Okay. Now you will simply go and do return position. Right. So that is very simple how you are doing right shift on XOR of M and N. Okay. So we can write this code also. Again, same thing. Just make it right shift and you are passing XOR only. So this right shift, small r. It is taking the XOR of M and N and I am initializing position with 1 initially, position equal to 1. Okay, and then while your this number capital X, let me write it N only. This is sometimes I miss writing capital X. Okay, so while your N, right, you are doing what? N bitwise AND with 1, right? So while N and 1 is equal to 0, till that time you are incrementing the count of position and doing a right shift on 1. Is that fine? You are doing N and 1. This is N, this is 1. You are doing its AND with it. You found a 0. So till you are getting 0, 0, 0, 0, you are doing the operation of what? You are first incrementing the count of position and you are doing the right shift on that X and repeating the same thing again. So I can write a loop for it. So you are first of all making right shift on N, and new N will be N right shifted by 1, and you are incrementing the count of position so that you know which position you will be finding 1 finally. Once you are out of this loop, your position will be at that position where your bit in N is 1. That is why your N and 1 will not be 0 anymore. So you will simply return that position. So position plus plus. Okay. Then you return position. Have I initialized position? Yes, I have. End position equal to 1. Also, if your N is 0, return minus 1. This is the second approach. Both the approaches you should be knowing. So this bit manipulation questions are not about how much programming you are doing. It's mostly about this bit masking, bit logics completely. Okay, so that is all about this problem. Let me see if you guys have any doubts. If you have any doubts, you can ask me. Let me see. So I think there are no doubts and we are live also. Well set. Okay, so that is all about this problem. You can use the same approach, the second approach I told you for this question also, only this will remain same, and the next things will be exactly what you have done here. Okay, all of these things you can solve that problem with this function also. Okay, so that is all about this problem, guys. See you all in the next lecture. Thank you everyone. Bye bye.